have four papers. Okay, so we have four papers, and Daniel Parra will begin. So 20 minutes, and take it away.
So thanks. So yeah, I'm also happy to be on the only session of live experiments in the conference, and I'm happy to share this time with you. So I will present something that it's already finished. So it's a project that's already published. That was not ideal, but when I submitted, I didn't know that it will get published so quick. So I will present this paper. Thanks. Yeah, that's not bad news for me, at least. So this paper, I'm on the market this year, but this paper is not my job market paper. My job market paper was not finished at the moment I did submit to LASEA, so I'm presenting this today. This is a joint work with Tilman Fries, Urin Nisi, and Agne Kajashkaite. Sorry, I cannot. Yeah. So why studying lying? I'm presenting a paper about lying and observability. And why studying lying? So there are two possible motivations. The typical one is the right-hand motivation. That is, there are some papers that shows that is correlated with corruption, and the lying could affect tax evasion and corruption. Another motivation that I can use is that lying can make markets fail. So imagine in a asymmetric information situation like the lemons market, one assumption for the lemons market making the market in general failing is that the seller lies about the quality of the car. But if people don't lie, the market failure won't happen. So the two motivations for the broad literature is that one, it makes possible that information asymmetries make market fails, and the other is that it's also correlated with general corruption and tax evasions in countries. So what we know so far is that in general, these models of, for instance, the markets of lemons, simplify the agent in a way that assumes that people only make a cost benefit in which if I lie and get some benefit, I will lie anyway. So the people don't feel bad by lying. However, there is some literature that shows that in general, there are people that prefer not to lie. And we will call this psychological cost of lying. So there are some models that shows that some people, even if there is no possibility of punishment, decide not to lie because more likely they have a psychological cost of lying that could be divided, for instance, in intrinsic cost of lying and reputational cost. And I will talk a bit more about it. So one example of this is, as I told you before, in my job market paper, I show that there are people are lying averse, so people they don't like to lie, but when they benefit others, this cost decreases. So people are more willing to lie when they benefit others. So what I'm showing here is that lying is a preference that has several components, and that it's interesting to study these components because it affects some economics outcomes. So this paper is really more methodological. So what I will show is basically a broad picture of the literature online to trying to put or to locate our paper. What is this contribution of our paper? So we have the first experiments where these experiments that use a deception game, or also called sender-receiver deception game, that was introduced by Nisi. And in this paper, in this game, basically the experimenter has a random draw that is shown to the sender, and the sender sends a message to a receiver, and the receiver needs to report either A or B, but the true outcome is only known by the receiver, or let's say that these payoffs are only known by the receiver, by the sender, sorry, and the receiver only can say A or B. Here, the sender can deceive the receiver to make him telling the more profitable outcome for him. And here we have two components in the willingness to deceive or willingness to lie. One is the social signaling cost, that is that the sender may want to appear honest to the eyes of the experimenter. The receiver won't know what was the real state, but the experimenter will know. So there is a social signaling cost or reputational cost. The second one is the self-signaling cost, and it's maybe the sender will feel bad if he has to say A, but says B to the receiver in order to get more money. So it's not only about money, but it's also about preferences to be honest, and divided in social signaling to the eyes of the experimenter and self-signaling to the own eyes, let's say, or to in comparison with their own norms. A second experiment that is used widely in the literature is this Fischbacher-Formenhuisi. In this paper, what participants do is just draw a die, and they get paid 1 if they draw 1, 2 if they draw 2, 3 if they draw 3, and so on and so forth. So in this game, we are no longer knowing what is the decisions of the participants. So we don't know whether participants are honest or dishonest, but we rely on aggregate decisions. So we give them more anonymity. Here, this privacy reduces the social signaling cost because the experimenter won't know whether an individual lied or no. But here we also have a component in which the participant can send a social signal by reporting 5. So imagine I am reporting a 5. So why I report 5 and not a 6? Probably in the eyes of the economic theory, reporting a 6, so lying to report a 5 doesn't make any sense. Because if I would lie, maybe I would lie to report a 6. That's true only if 5 doesn't send any signal. But given that others doesn't know my random draw, it could be the case that the experimental only thing that liars are those who reported 6, but not those who reported 5. So reporting 5 could be a way to say, maybe I'm not lying, maybe I draw as 5. That's so here we can play with this, and some models shows that partial lying can be explained by this reputation or social cost. Then what is the research question of the paper is whether varying these social signals possibilities affect honesty in cheating games. And we will also look how this affect differently women than men. What we did was varying the observability of the random draw in a die roll game. So we vary whether we see or not the die roll and the report. And then we also vary whether we see the report. So we have in total 5 treatments. I will explain it quickly. So I will start with the basic game, that is the traditional die roll game. Here we have participants got a die, they draw the die. If they report 1, they get paid by 1. If they report 2, they got paid 2, and so on. However, here we gave them an envelope in the desk with the total amount, maximum amount they can get, and they pay themselves. So they take the money, and then they go to the experimenter, return the envelope, the experimenter check that the money it's okay with the number they reported, and they leave. That's the only variation to the traditional, the envelope. And I will show you why I need an envelope. It's just for making all treatments comparable. Then we did exactly the same, but we include an observe game. In the observe game, participants roll the die and report to the experimenter in the same way, bringing back the envelope saying, I draw a 3, look, there is the left money there and left. However, the experimenter was behind them when they were rolling the dice. So they were instructed that the experimenter will go desk by desk in the lab, and we say, you can draw now, and the experimenter did that with each participant. However, the experimenter didn't note or anything, it was just physical observability. We don't have data on whether, or we don't have data about the random draws. We only have this variation where the experimenter was observing them, but not taking note or registering the actual random draw. In this change on the random draw, we also have a super observe game that was exactly as the observe game, but now the experimenter note and participants knew that the experimenter was noting the random draw. So here in the super observe, we have observability in the report, but non-observability on the random draw. Sorry, the other way around. We have observability of the random draw and observability of the report. We have all observability here. Then in the other side, what we did was doing a double-blind experiment in which we have these envelopes we use in the other treatments also, but now they don't bring back the envelope, but they just put the envelope in a big box outside the lab, and they left. So now in the double-blind, we don't see either the random draw or the report. And we included, I will say, a robustness treatment in which in the envelope we include fake coins. So we have the 6 euros coins plus 6 metal coins, just to check whether they care about the sound of the envelope or anything. That was just because we were surprised by the result in double blind, and we wanted to check whether the logistics made something change, but no, at the end, it was just a robustness check. So we run this experiment in Berlin. It lasted about 30 minutes in total with all the logistics. This is mostly because we were checking everything, and also in the sessions where the experimenter needed to go to each desk, it took some more minutes than the traditional die roll games. We have run this on 2019, and we have about half of female and half of men on the sample. So the results, what we found. So we found basically that line was less in the observe, but was the same on base. So comparing to basic, but was the same between basic and double blind. And this was already striking because we were expecting something like more order or more line in double blind and super double blind than in basic. And here that was a bit striking. So the side of the super observe, it's clear that we expected they line less because now we can detect liars, and there are another experiments that shows that. But one important thing is that the observed, not the super observed, but the observed, even if they knew that the experimenter didn't record the random draws, just the just the fact that the experimenter could remember or something like that already decreased a lot lying. In the super observed was basically lying to the eyes of the experimenter afterwards to claim some money. So that was clear. That was just also checking what was happening there. But in the double blind, with the traditional models, that didn't make that much sense in the sense that if here I cannot social signaling, why I'm having the same line as in the standard game. One good news here is that even if in basic we don't use, or in the traditional experiments online, we don't use double blind, or we don't check for this before a lot, it seems that even if we will do that, the results will be the same. Also, we have already in basic very high line rates, and maybe could be some ceiling effect here. But yeah, what we found is a robust effect of observability on the random draw, and no effect when we deliver total anonymity on the random draw and the report. Regarding partial line, this was also striking, because we found basically that the participants here in observed and super observed, in super observed in general, they didn't lie partially, and this makes sense because they cannot social signal anything by reporting 5. So here, drawing a 4 and reporting 5, given that the experimenters already knew the random draw, didn't make any sense, because they already are revealed as liars. They cannot say, maybe I'm good. So here, this makes sense. Here, what we were expecting was that, again, people or participants didn't lie partially, because again, they cannot social signal in anything. But here, our main explanation, or our main conjecture, is not explanation, because we cannot prove it, is maybe suggested in the paper by Duffenberg, participants already internalize some social norms, or they already internalize this norm of being honest, and some of them behave as if they were their own spectators. Because in the traditional models, we cannot explain why in double blind partial lying still existing. Finally, we also found that women in general lie less than men. However, the differences were not affected by observability in general. We proved this with this regression, where we have the interaction effects, and we didn't find significant results for women and men. We only observed that in general, in observed treatments, people lie less. So to wrap up and to summarize what we found in this paper, that is, again, a very methodological paper applied to the line literature, is that increasing the random draw facilitates honesty, whereas increasing the reports observability has no affected behavior. And it has an important implication, methodological implication, for experiments also online that will be run online. I had the problem here that, given that observability of random draw make people lie less, in online experiments, it's important to make credible to participants that the random draw is not recorded. So my best advice for that, and I did that on my job market paper and it worked really well, is using mind games where the random draw is on the mind. If not, it's really difficult to find treatment difference, because participants are really reluctant to lie in these situations. Here I already said that. that maybe participants already internalize or people already internalize the preference to appear honest and behave as if they were observed. So thank you so much, and I hope I did it on time. And
Yes,
if you want to read the paper, you can go to my homepage, and if it's not there, if the published version is not there, you can email me.
Okay,
Thanks a lot.
so if there are any questions for Daniel, you can either reach him directly or reach him through the chat. But we need to move on to
Okay,
the
thanks.
next presentation. So thank you. So if you can stop sharing your screen. Next we have Jiwei Zheng from the University of Lancaster. So okay, so I think
yeah,
okay,
can you
20
see
minutes.
my screen? Yeah.
Yes, we can see
Great.
your screen.
So thanks a lot. Thanks, Manu. The research I'm going to present involves coordination games and the focal point. So probably you are not very familiar with the line of research about focal point. So what I'm going to do is that I'm going to first tell you some background about focal point and the coordination games. Then I'm going to tell you the motivation, research question, and experiment design. We have 2 experiments. Hopefully I can tell you both of them, and results and some conclusions. If I still have some time, I can tell you some exciting future studies I'm doing at the moment, and to see if you have any comments. So this is called a pure coordination game. Okay, you can see this is a very simple game. It's a 2-player 2x2 game, and if both players they choose the same option, they choose the same strategy, they can get a positive amount, otherwise they get nothing. Traditional game theory can tell you, look, this game has 2 pure strategy Nash equilibria and 1 mixed strategy Nash equilibrium, but game theory cannot tell you, traditional game theory cannot tell you which strategy you need to choose if you want to improve your coordination success. In Thomas Schelling's book, The Strategy of Conflict, he finds that if we attach some salient labels to the strategies, for example, we put an underline here for the first option, then people will use this salient feature to increase their coordination success. Basically, they will choose the underlined option and coordinate on the salient equilibrium. We call it a focal point. Intuitively, this is nothing special, but the interesting thing is game theory cannot explain why this is the case. Although this kind of effect has been repeatedly found in lab experiments, okay, is not consistent with what game theory says. So Schelling, he proposed a theory called the theory of focal point, trying to explain people's behavior. And this theory has been further developed by Robert Seddon and Michael Bacharach by means of team reasoning. And the core idea of team reasoning is the following. It says, look, when playing coordination games, instead of asking, what should I do? Instead of using individual thinking, these players, they ask, what should we do? So they use team thinking. Once they start to use team thinking, of course, they're going to find out the best thing for the team to do. And the best thing in the previous example, of course, is to choose a salient option, right? And then their coordination success will be high. However, in 2008, Crawford et al., they actually study the power focal point using battle of the sexes. And what they find is very interesting. They find that when there's a small conflict of interest between players, okay, battle of the sexes, I mean, one player favors this equilibrium and the other player favors this equilibrium. When there's a small conflict, the magic power of focal point disappears, or in many studies shows that it drops dramatically. Okay, and then Crawford et al. Says, look, probably people are not using team reasoning, they're using individual thinking, like level K, all right? They think their player is one level below them, and then they anchor their belief on their partner. But of course, in the real life, their partners is not always one level below them, okay? So their coordination success is not high in the battle sexes because they don't use focal point, okay? They just focus too much on the payoffs. And since there are two theories that can explain people's behavior in coordination games with focal points, a line of research trying to find out which one is better, team reasoning or like individual thinking or like level K. And the main finding is that it depends. Okay, in some contexts, like in pure coordination games, in the game I show in page 1, 10, 10, 10, 10, we call it a pure coordination game because the payoffs across equilibria and between players are exactly the same. Okay, in pure coordination games, people are more likely to use team reasoning, and in Battle of the Sexes, they are more likely to use individual thinking. So this is a previous finding. And the Battle of the Sexes is a very interesting type of game because it can model a lot of real world situations, right? If you think here are two examples. We know there's a conflict between the US and China. We know there's a Brexit. In both situations, it's not like these two parties, they don't want to reach agreement. They do want to reach agreement, okay? Reaching agreement is always better than not reaching agreement. But the reason, or one of the reasons that it's so hard for them to reach agreement is because there are many ways to reach agreement, right? Some favors one party and some favors the other party. And in terms of focal point, a lot of things in the real life can be seen as focal point as long as it's salient, right? For example, status quo can be a focal point or convention can be a focal point. So what we are trying to do in this research is that we are trying to find out a way to improve coordination success in the Battle of the Sexes with focal point. This is what we want to find, what we want to do. And how to improve the coordination success in Battle of the Sexes? It seems to us that if we can trigger team reasoning, if people thinking as a team, then of course they are going to use a focal point and the coordination success will be high. And the one thing we can do to highlight team reasoning, according to Bacharach's book, he also mentioned that, is to highlight the common interests in the Battle of the Sexes. Okay, let them focus on the common interest, but not the conflict. Actually, highlighting the common interest is not only a theoretical argument in Bacharach's book. In the real life, you can see here are two pieces of news I found in the internet that at the beginning of the conflict between China and the UK, you can see the Chinese government is trying to use this strategy. They highlight the common interest between China and the US, trying to avoid this competition or conflict, right? And in our research, to highlight the common interest in the Battle of the Sexes, we developed a new set of games. We named them as compound games. Okay, it's named after compound lottery. So next, I'm going to tell you more about compound games. But before I do that, I need to show you some terminologies I will use in this 20-minute presentation. The first terminology is a simple game. A simple game is nothing special. We developed this terminology just to separate it with compound games. You can see a normal form game is a simple game, okay? It's nothing special. This is a simple Battle of the Sexes, okay? The interesting thing is that the simple Battle of the Sexes can be decomposed into two component games. For example, the first one is the Battle of the Sexes, and the second one is so-called pure coordination games. You can see 7 plus 4 is 11, and 6 plus 4 is 10. Okay, the Battle of the Sexes tells you that, okay, there's a conflict component, and the pure coordination game tells you that there's a common interest. Of course, both games has focal points in this case. Okay, however, if we ask people to play these two component games, you can see the reduced form of these two games is not the same as the simple Battle of the Sexes, right? It is different. It's a 4x4 game rather than 2x2 Battle of the Sexes. This is apparently not what we want. What we want is to highlight the common interest. We don't want to change the game, right? But we still give a name of these two component games together. We say these two components together, we call them Cartesian game, but it's not important, okay? The important thing is that we want to develop compound game. So we put a constraint on the Cartesian game. We say, look, you can play these two component games derived from simple games. However, there's a constraint. You will have to choose the same action across these two component games. For example, if you want to choose A, you have to choose A in both component games. If you want to choose B, you have to choose B in both component games. You cannot say choose A in one component game and B in another component game. It's not allowed, okay? If we put a constraint on this two component games, then we see the reduced form is exactly the same, or mathematically speaking, or theoretically speaking, they're exactly the same as the simple game from which it is derived. We say these two component games, along with the constraint, we call them together a compound game. And the interesting question to ask is that although this compound game and the simple game, mathematically, they're the same, whether people will behave differently when they play these two type of games. This is the core. And of course, here are three more specific kind of research questions. First, does this decomposition highlight common interest and increase coordination success? Okay, probably we can observe that in the compound game, people are more likely to choose the underlined option than in the simple game. And the second is, does the size of the separated pure coordination game payoff matter? You can see in this example, the pure coordination game is a 4-4 and a 4-4. We can also do another decomposition, right? For example, in this example, the same battle of the sexes, we can say this component game is 10-10-10-10, okay? And the size increases, of course. The battle of the sexes, the size decreases accordingly. And the last question we want to ask is whether the order of the presentation or sequentiality matter. You can see in this compound game, the battle of the sexes component is the first and the PCG is the second. And in this example, for example, in this compound game, the pure coordination game is the first and the battle of the sexes is second. Okay, this is, we want to see whether the order matters. In addition to the battle of the sexes, we can also do the same thing for pure coordination games. We can see, look, pure coordination games can be decomposed into two pure coordination component games, or it can be decomposed into two battle of the sexes. So of course, there's a constraint. You have to choose the same action. So mathematically speaking, these games are exactly the same, but whether people will behave differently. Okay, this is experiment one. It is a big table, but the basic logic is the following. We find three simple games. We find a pure coordination game and the two battle of the sexes with different degree of conflict. Okay, sorry, I forgot to tell you that the way we name this compound game is always use a payoff in the box to the bottom left. Okay, so for example, this game we call it a 4-4-6-6 game, and this game we call it 4-3-6-7 game. This is how we name these compound games. So in the experiment design, we find three simple games, and then we generate some compound games from these three simple games. For example, in 10-10-10-10, you can see we can make PCG compound games, or we can make battle of sexes compound games. Of course, the size of the PCG games or the battle of sexes can change. The payoffs can change, right? And for the simple battle of the sexes, we can always we can always generate, for example, we always generate a pure coordination game and a battle of the sexes. We always decompose the game in this way. Okay, and of course we can change the order. You can see here the size of the pure coordination game changes. Okay, and the size of the battle of the sexes also changes. And the 9-12 battle of sexes, we do the same. It's just a degree, and it's a within subject design. Basically, we ask each subject to do all these games. Okay, so mathematically speaking, all these games are the same. All these games are the same, and all these games are the same. So this is a screenshot. You can see we ask people to choose an allocation between themselves and another player. This task one is the first component game, which is always located on top. And the task two is the second component game, which is always located at the bottom. And we see these two tasks are linked, which means you will have to choose the same option across two component games. Okay, I can tell you in advance, we don't find any effect on the size of the pure coordination games. So in the results section, I'm going to pull this game together. Okay, first let's see the simple pure coordination game and the two compound games derived from the simple pure coordination game. Okay, there are two types, PCG, and VOS. And this number shows the proportion of people, proportion of subjects choosing the underlined option. You can see in simple pure coordination game or PCG, a big proportion of subjects, okay, about 82%, 82.6% or 86.5%, they choose the underlined option. This is consistent with the previous literature. A lot of people will do that when there's no conflict, will choose the underlying option. However, if we decompose the games into two battle of the sexes, then the percentage drops to 74.3%. So it matters when you create compound games. At least the frame, let's say, the frame of the game matters, okay? And if you think about the battle of the sexes, okay, there's a simple battle of the sexes or a compound game, okay, in which the battle of the sexes is the first component, or the compound game in which the pure coordination game is the first component, okay? We see the proportion of people choosing the underlined option. We see in the simple battle of the sexes, on average, people are less likely to choose the underlined option. And in the two compound games, people are more likely to choose the underlined option. However, this difference is not statistically significant. Okay, we think, look, in this experiment, we present the two component games together. Although one is on top and one is at the bottom, okay, we show them together, we show them simultaneously. So each subject can see both component games simultaneously. Probably this is not the best way to study the effect of sequentiality, right? So in the next experiment, what we did is we show these two games sequentially. We first show the first component game to the subjects. And we say, look, you need to read this component game. You need to even make a temporary choice on this component game, okay? After doing that, we show them the second component. Of course, if they change their mind, they can change their options. Okay, they're changed. The reason that we want to do that is we sort of believe the first component game can shape people's reasoning. For example, if the first component game is a pure coordination game with focal point, probably people are more likely to use team reasoning. And after seeing the whole compound game, they will continue using team reasoning. Okay, they will carry on using team reasoning. However, if the first component they see is the battle of the sexes, probably the subjects are more likely to use individual thinking. They will ignore the underline. They will focus more on the payoff differences. And then after seeing the second component with a pure, which is a pure coordination game, they will carry on using individual thinking to solve the whole compound game. So this is the logic behind this design. Okay, so let's see some results. First, again, we see the pure coordination games and the two compound games derived from pure coordination games. Again, we find the robust results, okay? If you show the two component games sequentially, again, if the compound game contains two battle of the sexes, only 63.4% they will choose underlined option. However, in other two cases, in this two pure coordination game, compound game, or simple, two pure coordination compound game or simple pure coordination game, a big proportion of people will choose the underlying option. So this result is robust. And this result is quite interesting. What we find is, look, if in a compound game, if the first component is the battle of the sexes, then people are less likely to choose the underlying option. However, if the first component is a pure coordination game, then comparatively speaking, people are more likely to choose the underlying option. So this is consistent with our conjecture. Probably the first game, when they see it, when they consider it, when they even make a temporary choice on it, it can shape their reasoning, it can shape their decision process for the whole compound game. This is what we find. Okay. Here is a conclusion. I don't want to make it too long. So if we can, okay, in negotiations, if there are many things we want to negotiate, probably we can decompose a thing with an event with conflict interest into pure coordination game and the bet of the sixes. We can negotiate on the event that we have common interest, then reserve the things we have conflicts later on, okay? And our findings also suggest that probably our modes of reasoning can be affected by the first component game you see, okay? Here are some future studies, just 1 minute. You can see compound game, the idea I think is quite cool. You can even decompose Prisoner's Dilemma or Stack Hound game, right? If you decompose these two games, the compound game, you can see Prisoner's Dilemma can be decomposed into a high-low and off-diagonal bet of the sexes. And the Stack Hound can also be decomposed into these two components, right? And they look very similar, although theoretically speaking, they are very different games. And the question is, if we do that, will people's behavior when they are playing these two types, will their behavior be similar, okay, comparing to when they play the simple Prisoner's Dilemma and the Stack Hound game? Okay, here's something more, and thank you very much. Thanks for listening.
Hey, thank you very much. That was perfect on time. And again,
Yeah.
if anybody wants to ask Jingwei a question, you can send him a message directly, or you know, or just send him an email. Okay. So thanks. So now we move on to Hernan. Thank you. The very nice peer presentations. Hernan Bejarano. Think that you have to stop sharing screen, G-Way, and so thank you. And so now, Hernan, the floor is yours. And you have 20 minutes. I'll send you a private message when you have 3 minutes left, okay?
Okay, let me know if you see my screen.
We can see your screen, but it's a little weird.
Okay, let me see.
We see a notepad.
Okay.
Oh, now
yeah, I
we
have
can
to
see your
switch.
screen.
I have to switch this place.
Now we can see your screen.
There you can see it. No, so thank you
but it's
everyone for being here.
But
Thank
the
you
slides
everyone
are super small.
Oh, you are seeing it small?
Yeah.
Oh, let me see. Now?
Yeah, now they're bigger, but still on the small side.
Let me switch. Yeah, I have to switch the share screen configuration. Probably.
Okay.
Stop sharing, and then I will share. Sorry.
No problem.
Yeah. Let's see. Now better?
Now it's better. There you go.
Okay. So let me start presenting. So thank you everyone for being today here. And this is a joint research with Joris Gillette from Middlesex University and Ismael Rodriguez Lara. And this has been funded by IFRI, a research that has been funded by IFRI. And it's based on a research agenda that analyzes the effects of shocks and inequalities in one game in this case, but an agenda that we aim to expand. We started with the trust game, and we started with negative shocks based on the motivation of natural disasters and its effects on trust and solidarity. And then in this paper that we are presenting today, we move to analyze the effect of positive shocks on interest. Basically, we moved from the field to the lab. My first research on this topic was on the field after the natural disaster in Chile in the year 2010, and then we moved from the field to the lab to take advantage of the control that we have in the lab in issues of separating the effects of wealth or endowments and information that all these features are mixing in the field when you are facing a natural disaster. The idea of analyzing the positive shocks is like, because it seems like looking at the bright side of the problems is usually not so attractive, but we thought there might be something there. In addition to that, there is research on different kind of fields that talk about the importance of positive shocks, particularly in the fields of our organizational economics, in issues such as like creativity and these like eureka moments or shocks of productivity, and in the field of agricultural or economics, in issues regarding like the positive shocks in the pricing of agricultural products. I see Juan, like he's one of the experts on these things. No? So positive shocks, we know a little bit about the effects of positive shocks. Particularly, we know about them in these two concepts, two fields that I just mentioned. No, so in another research that we published last year, well, it's got published this year. Basically, it's a gift exchange model in which like we have also positive and negative shocks in the context of an employer and an employee. What we see is like when there is a positive shock in the price of the good produced by this micro nano firm in the lab, in a real effort game, employers do not transfer the increment in their revenue fairly to employees. No, so they absorb most of the gains of the shock in the price, and they do not take advantage of the positive reciprocity that the employers will present in this context if there is some kind of gift exchange. No, this argument actually has been analyzed by other authors in the context of gift exchange models, but also in another type of games. And also has been analyzed by people focusing on developing countries' markets, just as Jan Chandran that says that because there is some kind of reference in terms of the wage that employees receive, then the interaction between reference and the shocks on prices might be acting as a mediator that does not allow to transfer the positive benefits of all the shock into the employees. No. So as I say, we ran these experiments in the lab. We ran a total of 18 experimental sessions with 408 students. So these are like 204 pairs. We conducted this in the Economic Science Institute at Chapman University, and we tried to mimic what we did in the field. Similar to what Daniel said, that he needed an envelope. I will show you how pictures of what we did to try to replicate things that we hope to take later to the field whenever the situation allows it. So we separate first players and second players of the trust game in different rooms. And we did a hand run experiment. It's only one choice because it's a hand run and it's with paper and pencil. It took around like an hour and a quarter. Students hated that, but that's another topic. We told them that they couldn't do anything. They couldn't use the cell phone, and that was like a crisis. So then we allowed them to do their homework after they made their decision in the lab. No, so this was the setting. We put envelopes in each one desk, and the envelopes have the number, and if they were player 1 or player 2, the number of the pair. We have experimental dollars because when we run this in the lab, in the field in Chile, we use real money in the envelopes. In this case, we use experimental dollars. Notice that this make, in our belief, the shock more salient. It's a physical implementation of the shock. So we will roll a die, and if the result of rolling the die in front of the player 1 is 1, then they know for sure that is perfect information that the endowment of the second player is going to change. The second player is going to see this change in the endowment because they will put a note that a pre-written note that we have, like say the result of the die was X, and then your endowment will change or will not change. in the case that they will change, we will take the envelope, the envelope with this note inside, and then we will increase the endowment of the second player. No? So we believe that this is like one of the most salient ways of implementing shocks in the endowment. We noticed that it was very salient with the negative shocks. We saw, because one of the lab coordinators had to take the money, the experimental money, out of the endowment, and we saw the faces of the subjects. We think that this might make less easy to replicate our experiment, but that was a business that we were willing to take. This is the number of observations that we have in each one of the treatments, because we want to decompose the effects of inequalities from the effects of the change in the endowment. So we have, notice, we have like four treatments, 2 baselines, and 2 treatments. No, so we have a baseline where the endowment of first and second mover is the same, a baseline in which like the endowment of the second mover is poorer than the first mover, and we will arrive to the same situations, but given that both of the second movers in our treatments start with the lower endowment, some of them will get their endowment increased to 21st if the outcome of the die was odd, and some of them will remain the same. So in other literature related, this will be like being exposed to the positive shock, but not being affected, or being affected by the positive shock. So we have around 50 observations in each condition. So now I will walk towards what we try to do, and something that we believe that is important. This modification happened in our first paper with negative shocks. One of the modifications that was incorporating inequality aversion into the model of the subjects. And then in this one, because we noticed that some of the effects in our negative shocks paper were not being possible of being explained just by the presence of inequality aversion, we incorporated another concept more, that is like reference dependence in terms of the endowment. So we start with the payment functions that we induce in the experiment. These are the traditional ones. We have the multiplier of 3, and then we add inequality aversion. And now, in addition to that, we add a reference point. There is a whole discussion. We have a section in the paper regarding. I can send you the paper is under review. I can send you the latest version if you want. There is a whole discussion of how to incorporate a reference point in terms of the endowment here. You have a more traditional thinking about, the initial endowment is your reference point, or you can think about the distribution. It's like the initial endowment or the increased endowment, and with what chance. And that's more in the Botton-Koseki kind of environment. The predictions do not vary considerably independently of which type of reference dependent you want. They change in the magnitude. We took this implementation in mind of how the reference dependence of the player 2 behaves. And I'm going to start with the predictions, the theoretical predictions, and with the results from the point of view of first player 2, where there is not a strategic uncertainty about what player 1 is going to do, because I receive already the money and I just have to pick how to reciprocate. Then notice that when you have to think about the predictions and the behavior of player 1, the issues become more complicated, because now you have a strategic uncertainty, and you have beliefs about the preferences of player 2, and things can become more complicated. Because of our original implementation, they have a belief elicitation. We don't have belief elicitation in this experiment. That's one of the areas in where we would like to expand. We are doing something with belief elicitations and shocks and inequalities, but in a dictator game. and we will hope to expand it to other games later. So we have this implementation, and we assume that there is some kind of like some kind of loss aversion. No? So notice that if you derive the optimal behavior of the second player who are inequality adverse and have a reference dependent utility, that ended up being something that comes out in two terms of this derivation, assuming all the things. Basically, when you have a change in the endowment, you have some effect there. And when you have a reference point and a potential change in the endowment, then you have another things. Both of the things are used to derive our behavioral predictions. As I mentioned, I will start with the prediction for the second player, and then we will move to the predictions for the first player with some assumptions behind. No, so the first prediction is like, if second movers are inequality adverse, they will return less in the cases, basically in the cases in which they are poorer. That means like in the way that we name the treatments in the paper, in the baseline unequal and the baseline equal treatment. Additionally, in the baseline unequal and the bonus unequal treatment. In addition to that, if the second movers are inequality adverse and have a reference the dependent utility, now is the part in which we start to decompose the difference of the mechanism generating this equality or inequality in wealth. No, so what we have now is like they will send similar amounts in the bonus unequal, in the case in which like they did not become rich, and the baseline unequal treatment in which they started in a poorer position, but they will return more when they become new rich. So and for the first movers, we did two types of predictions. One is like based on an idea that they are altruistic, and the other type of idea is like they are selfish, but they have belief regarding the other players not being selfish. No, so the first prediction is like, if the first mover are altruistic, then they will sell more to the poorer people. No, and this is independently of the mechanism generating the inequality. The second prediction is like, if they are altruistic and they believe that the second movers will obtain some utility of becoming richer, basically of having an increment in that, so they will send less money to those that they started being equally rich to them than to those that they become new rich. And finally, if we believe that there are some kind of self-interested first mover, but they have some belief regarding the second movers, then they will send more to those that have the same amount of endowments at them, independently of the mechanism generating that. And then they will, if they are interested, and they also anticipate that second movers are more likely to reciprocate when they become richer, they will send more to those that are new rich. In general, like, we can summarize the results like this with more words that we can talk to our friends, and I will move forward to the results. So here you see on one side of the screen, you see the two treatments with the same endowment for player one and player two. And in the other side of the screen, you're saying the two treatments with a richer player one and player two. And there is a negative significant difference. And now we analyze the difference between those treatments that have the same way of generating the inequality. No? So we observe difference between those that are richer second movers and those that are poorer second movers from the onset. And then we also observe difference between those second movers that have the same amount of endowment, but they started, the ones that started as rich as the first mover send less than the ones that become richer. That goes in the direction of our prediction. And then the difference, of course, as a result, the difference between those second movers that become richer and those that stay poorer is much stronger and more highly significant than those the difference that those that started richer or poorer from the onset. So those are the results from the second mover, not the strategic uncertainty, just will be reflecting something of how their behavior changed when their endowment changed. No? So for the first movers, it's a little bit more difficult. Basically, I will give you a spoiler alert. First movers don't seem to recognize this behavior of the second movers. So amounts are by the first movers. What do we observe? We observe that they send more to those that are richer than those that are poorer. And this happened irrespectively of they starting on the onset. But now the difference is like when they find a second mover that just become rich, that's why the title of the paper, they send them less. And this difference is statistically significant. And because of that, there is also a difference in the opposite sense that those that start richer and start poorer, that between what they send to those that become rich, they send significantly less than those that remain poor. So those are the results, and the results partially support the theoretical model. And I think that for the sake of time, is like wrapping up. Shocks influence the strategic behavior of player in the trust game. We knew that from previous papers that we have and from other papers that we have. The effect seems to be role dependent. First and second mover do not consider the shocks in the same way, and this occurs in the context of the lab where there is full information and perfect information of the occurrence of the shock. And we believe that there is an avenue or route for new research that include environments where we start to move closer to the field, incorporating uncertainty and ambiguity, and maybe even some private information. But before doing that, like we need to improve the theory, no? Because like the theory explained just a little bit, and that's all from me. Thank you, everyone. You have the
okay. Thank you very much, Hernan.
Okay.
Very nice. So now I will try to, everybody was good with time-wise, so I'll try to stick and not change the okay. So I'm hoping you can see my screen by now, because now I'm on the other side. Okay, so okay. So put my timer. So thanks for everybody who came to this session. Last talk of the session. This is a joint paper with my previous colleagues, Ignacio Ponda and Sergi Yüksel, and the paper is entitled "Mental Models on Learning: The Case-Based Rate Neglect." Okay, so the idea is the following: there's a large literature documenting many biases in decision making. Okay, so we know to what extent these biases, some of these biases exist, when not, and so on. What we know less of is how these biases interact with feedback, to what extent these biases persist, if people can learn from feedback, and to what extent an initial misconception, an initial bias essentially gets in the way of interpreting the information you get from feedback. So this paper is essentially a proof of concept of this idea. And we do it with base rate neglect because it has some properties that are useful to study. But just in case you don't remember the particular example, let me go through it. This is an example from Kahneman and Tversky in 1973. The idea is the following: there's a prevalence of a disease in the population, 15%, and you know this prior. Then there's a test that you can take, and with 80% chance, it is reliable, meaning that the test is positive with that chance if the person is sick, and the test is negative with that chance if the person is not sick. And then you're provided with this information on essentially a prior and the reliability of the signal, and people are asked, well, you got a positive test, what's the chance that the person is sick? So they ask essentially on the posterior. And now this involves computing a relatively trivial Bayesian benchmark. So what's the probability of being sick conditional on a positive test result? You can compute this thing. It turns out here it's 41%. And the reason why, I guess these parameters were selected back then is that even though you get a positive test result, the probability of being sick is still less than half. And the reason for that is that you have these very, very low prevalence baseline. The prior is relatively low. So that's the Bayesian answer. But the most common answer that people tend to give in this case is known as base rate neglect, because people tend to say 80%. Okay, so this is one of the failures of Bayesian updating. It's well documented. It doesn't happen with every parameter. But the point of this paper is not to try to understand why base rate neglect takes place. That's essentially what the literature has been trying to do since 1973. What we are more interested in studying is the situation of somebody who, for example, may have base rate neglect, who may give 80% as an answer. The doctor who, given these primitives, they make a mistake and they think that with 80% chance the person is sick when they get a positive test result. But if you think of a doctor that makes this mistake, as has been documented in the literature, then this doctor keeps on getting patients, and the patients arrive, and the patients and the tests results are there. And so in time, they presumably will collect evidence that will challenge this very wrong belief. And we're not so interested in why the belief starts in the first place, but whether information can essentially help people overcome these bias. So one point, I think it's the boring question in this paper, or relatively boring, but not boring, but it's the second order question, is whether with information people become Bayesian. So it is, do people in the long run behave as if they are frequentists, that they may not understand Bayes' rule, but they essentially use the data and they become frequentists? The answer we're going to give here in our data is that there's convergence to the benchmark, but that's low and partial. And the reason why I say that that's not the most interesting question, because from our purposes, the most interesting question is whether starting with the bias gets in the way of learning from feedback. And that's a more difficult question. I'll show you how we try to get at this. But just to give a preview, our answer is that yes, if you could remove base rate neglect from the person's brain in a way, their learning would have been faster. And in fact, those that are initially displaying base rate neglect, we find tend to pay less attention to the feedback that they receive. So essentially, the story would be that you start with a bias, but you are unaware of that bias. You think that you have it right, so you don't pay attention to the data, so then you don't learn from the data. That could be a way of summarizing it. And then a question becomes, can this type of thing be corrected? Can somehow these beliefs be changed? And the answer is yes. So what we show is that the same information that people have been ignoring because perhaps they were convinced of their initial answer, when you present that information in a way that unequivocally challenges base rate neglect, people are happy and willing to give it up and to provide an answer that corresponds to the data. So the paper shows it can be corrected, but let me quickly try to explain what the main highlights of the paper are and how we get at this. So the main task in the experiment is essentially the one I described, except that we don't use a disease as the base, as the environment. We run these experiments prior to the pandemic. So, but in any case, we thought that we wanted a slightly more abstract setting. So there are 100 projects. We tell people 15 of the projects are successes and 85 are failures. One project is randomly selected, and the task that they have is to assess the chance that this project randomly selected is success after knowing some test result. So, you know, if the test is positive, what's the chance the project is a success? And they know that the test result is either positive or negative and has a reliability of 80%. So essentially, the first thing that people will do in our experiment is a replication of the standard base rate neglect result. So again, we don't want to understand why this happens. We just want to make sure that we have a starting point where the bias is present, and we're more interested in understanding to what extent this bias can be reduced or eliminated. For that reason, people, as a surprise, we tell them, oh, now you're going to do this thing for 200 rounds. And in each round, you're going to get feedback on, on what happened the previous round. So you're going to collect data. So essentially, this is a screenshot. You make the first round decision. We use the strategy method here. So we ask people to give us a posterior conditional on a positive test result. The correct answer here would be 41%. You can move this up or down depending on what you want, but here I'm representing the correct answer. I didn't mention, but if you get a negative test result, remember that the prior is 15%, the test is relatively reliable. So the posterior with a negative test result is just like 4% chance of a project being a success. So we ask people both posteriors, so we ask them for both beliefs. And after they submit the beliefs, and we introduce the fact that there's going to be these 200 rounds, well, they can get feedback. So this is the feedback they get the first round. They say, well, the test round is positive, the project round is a failure. And so they will learn that they can move on to round 2 and so on. This is, for example, in round 5, after they've made their choices. And here I'm illustrating the choices that a person that is completely ignoring the baseline, the base rate would provide. So 80% chance of success, conditional positive test result, and 20% chance of success, conditional and negative test result. The person would still collect feedback. The feedback would be accumulated here on a table, right? So I can see round 1, 2, 3, 4, whether the test was positive or negative in each round, and whether the project was a failure or a success. Okay. So for pyramid purposes, we're using we're incentivizing beliefs using one of the standard methods, and I'm ignoring all of those details in the interest of time. So this is probably not an easy problem if you still have to process this data. That may not be straightforward. But you can see how, at least from just the things I've given you so far, that we could look after 200 rounds whether people are close to the Bayesian benchmark in terms of the belief that they report or not. Like, that's something that you can do here. But the main goal is to study whether initial misconceptions can impact learning. Now, to do that, what you would like is an environment where learning is still possible, but where initial misconceptions are removed, where you can still learn from data, but where you cannot be biased. So that's the treatment that we need to construct. And so the way we're going to do it is that we're going to have a treatment that I'm going to call a treatment with no primitives, where the problem is described exactly as I explained so far. And that's going to be, what I've explained so far is the treatment that we're calling P for primitives. But in the treatment with no primitives, we're just not going to tell the subjects the numerical values of P and Q. So here's how it is. It's like the primitives, I said 15 projects are successes and 85 are failures. In the primitives case, we tell people, well, some projects are successes and the remaining ones are failures. With respect to the test result, we tell them in the primitives case, well, the test has a reliability of 80%, while in the no primitives case, we just tell them the test result is either positive or negative and has a reliability of Q%. Now, clearly, the first time that people make decisions in these environments, they have to take a guess, and we tell them, you don't have enough information, so just take a guess. But the point is that because we don't give them the 15% and the 80%, base rate neglect as an answer is not feasible. And so the fact that we are not telling them the numerical values makes base rate neglect not an option. However, they will still collect these 200 rounds of data. So the table for people in this treatment has the exact same form as the table for people in the treatment with primitives where they know 15% and 80%. And to some extent, you can think of this treatment where people are not told these values as a treatment where all that people have is the data they collect in this table. So it can serve as a benchmark of how well humans can do when all that they have is the table that collects information on the right-hand side. So that's the main manipulation and the main comparison, because in the treatment with no primitives, people can't have the bias. And so now the first answer in this treatment, the first round, is not very informative because it's just a guess, but we would like to know what happens after 200 rounds. You know, these are people that have the opportunity to learn from data, but did not have the opportunity to start with these bias, okay? And so the comparison between these two treatments is where the crucial aspect is. So we go to the results. So I'm going to show you the results essentially in a picture like this, where on the horizontal axis, I'm going to have the belief that people report conditional on a negative test result. And on the vertical axis, I'm going to have the belief condition on a positive test result. So theoretical benchmarks, if you're doing perfect base rate neglect, you will say 80-20, right? So notice that the crazy aspect of this is saying 20% after a negative test result means that you think that success is more likely after a negative test result than the prior of 15%, okay? So Bayesian point is 41 and 4, and it's down here. So what I'm going to show you now, so, you know, we can replicate the results. Most people in the treatment with primitives are base rate neglect, but not everybody's there. So on average, people in the treatment with primitives, that it's going to be this red dot on the first round are here. The average at the aggregate level is between, say, 64 and 22%. There's 56% of people that are exactly there, but I first want to show aggregates, and then I'll decompose this a little bit. So that's where they start. You know, they start relatively far from the Bayesian benchmark. They are relatively closer to perfect base rate neglect, but you know, these are people that have the primitives and they have data. And the first thing that I would like to see is to what extent they learn in time. So that's where they are after they collect 20 rounds of data. You can see that they are moving in the direction of the Bayesian benchmark. So they're getting closer to being Bayesians, at least from a frequencies perspective. 40, they're getting closer. But at 60, they kind of go back, 80, 100. So let me remove the points in between. So after 100 rounds, they're moving in the direction of the Bayesian benchmark, but they're still relatively far. So now let me show you what happens with the people who only had data. Okay, they did not know that P is equal to 15% and that Q is equal to 80%. They knew that they were constant, but they didn't know the numerical values. So these are people that only have data that is generated structurally with the same parameters. So this group I'm going to track with the blue numbers, and in round one, they start here. Now it's close to 50-50, but not exactly. But there's a, you know, they're very far from the people in the other treatment. They're far from essentially every point. But after 20 rounds, there's no treatment effect. And after 40 rounds, they keep on learning. So after 100 rounds, the people, you know, these people are not perfect. It's not easy to read perfectly the information in that table. But there's a treatment effect after 100 rounds that remains after 200 rounds. So one more 100 rounds doesn't do a difference. But the people who did not have the primitives are relatively closer to the Bayesian benchmark relative to the people who had the primitives and the data. And there's a treatment effect. And there's a difference between these two treatments. So this is our first result. So beliefs in both treatments move closer to the Bayesian benchmark as we go from round 1 to round 200. By round 200, beliefs are significantly different between the primitives and no primitives treatments. And beliefs are closer to the Bayesian benchmark in the treatment with no primitives. Okay, so if you think about it, these people that have less information because they don't have the value of P is equal to 15% and Q is equal to 80%, after 200 rounds of data, they are relatively closer to the correct posteriors relative to the people who, in addition to having this data, also could have computed the correct posterior from the get-go. Okay, so I showed you aggregate stuff. That aggregate stuff can be, that doesn't convey the heterogeneity that is in the data. So I'm going to briefly describe the heterogeneity. So this is a treatment where people had the numerical values of P and Q and the data. In round one, 56.3% of people give you the perfect Bayes rate neglect answer. There's 3% of our subjects that give you 41 and 4. And Bayesian people give you 41 and 4. Like there's not lots of people that are really, really close to them. And then there's some people all over. But after 200 rounds, you can see that the aggregates that I was giving that were about, in the middle, between the perfect Bayes rate neglect point and the Bayesian point was not very representative, because essentially you have two groups. You have a group of people that are, here doing the perfect Bayes rate neglect point, and a group of people that are closer to the Bayesian benchmark. So the average is in between, but there's not many people that are exactly there. What I don't have time to show you, but what we show in the paper, is that essentially the people that are close to a perfect Bayes rate neglect point after 200 rounds are people who start at the perfect Bayes rate neglect point, so saying 80-20 in round one. So there's lots of persistence here. There's some people who learn, but essentially these subjects are people who give you after 200 rounds an answer that's pretty close to the answer they gave you in round one. And now this may be less weird than it sounds, in the sense that if you're giving the Bayesian answer and you say 41 and 4, you have it right. Why would you look at the data? You would keep on giving the same answer and just ignore the data. So if you have the wrong answer to begin with, but you think that your answer is right, you would have the same behavior and ignore the data. The other treatment is not, we don't get the same behavior. So this is the case where people only have the data. Most people I mentioned were saying 50-50 to begin with. But after 200 rounds, you see that actually most people are close to the Bayesian benchmark. And here, if we were measuring distances relative to the frequencies that they observed, which can differ from the long run, the convergence point, they are actually closer. So these people are much more adept at tracking data. So subjects in the primitive treatment who display Bayes rate neglect in round one, this is what I couldn't show you, but it's in the paper, are essentially driving the treatment effect in round 200, in the sense that if we didn't have these people who are essentially attached to the bias from that they started with, then there wouldn't be a treatment effect. So, in the interest, I have 1 minute left, so I'm just going to give you a quick overview of the other things that are in the paper. I mentioned I could show you that adjustment is slow and partial towards the Bayesian benchmark when people have the primitives. The results indicate that starting with this bias hinders learning, because people who do not know P and Q and cannot have a bias tend to process the data in a better way and get closer to the Bayesian benchmark. In the paper, we show that the reason why learning is slower is related to the fact that Bayes rate neglect subjects are not paying attention to feedback, and there's lots of evidence with respect to that. But we also show that if after they have done these 200 rounds, you show them a summary of the table that they have seen in a way that challenges beliefs, they readily give up on their beliefs, and there's no longer a treatment effect. So this bias can be corrected. And the last thing I wanted to say is that even though we have done these manipulations in the world of Bayes rate neglect, this is we think of this as proof of concept, and that you can actually take to other settings and study also whether other biases survive feedback or not. Okay, and with that, I finish. So I'm 10 seconds after my time, and I think that let me stop sharing. Okay, and I think that with that the session is over, and and you're free to go to some other room you wish to go. Thanks to all the presenters, and if there's anybody around, thanks to the organizers. Thanks, Henry, for helping us. And you can reach out to any of us via email if you have any questions, comments, complaints, or anything. Okay? Any final comments? All right.
Thank you, everyone.
Okay.
It was great.
Thank
Thanks.
you very much.
Bye.
Sorry, I sent
Oh.
I sent a message. I just
Yes.
wonder. I mean, missed this point. Is there any underlying mechanism that why less information leads to more Bayesian?
Well, if you're tracking the data, right?
Mhm.
If you're just tracking the data, it's not that you perform Bayes' rule. It's that you're computing the frequencies, right?
And what I mean, in the primitive treatment, you also have the data, right?
Yes, that's right. They could do it.
But why? Why they don't do it? Well, they
Well-
do it, but why they don't do it that good? I mean,
Well, I mean, the stuff that I missed because of time, what you suggest is that you say 80-20.
mhm.
That is wrong, but you're convinced it's right. So why would you look at data?
Oh,
You say, if the correct posteriors are 41 and 4, you say 41 and 4, you don't look at the data. Why would you? You have it right. The data are not going to show you anything that you haven't computed.
mm.
But if you start from the wrong place, but you think it's correct, right?
That means the wrong primitive actually destroys their
Right,
affects
so
their.
If you give me the bias and I start with the bias, but I am convinced I am not biased, why would I look at the data?
No, this is interesting because this reminds me. I'm sorry if
Yes.
I just a very quick. This reminds me a paper written by Robert Sitt and Andrea Izzoni. They also ask people to do one kind of related to anchoring effect. They ask people to do that thing repeatedly in the market. It's kind of a learning, and every time
Yes.
they have some feedback. And what they find is the effect of anchoring effect, the anchoring effect decreases, however, they don't disappear.
Mhm.
So they still exist, which means actually, if you give the people a bias at the very beginning, it's a kind of anchoring
Mhm.
effect at the
Mhm.
beginning. And the market experience, the market can decrease the bias, but the market cannot totally
Perfect.
eliminate.
That's super interesting. Can you
Yeah.
give me a reference?
Yeah,
Because
I can give you the reference.
that would be awesome.
I think it's called do markets review preferences or shape them? I just
Great.
type it here.
Okay, awesome.
Yeah, I think that may be relevant to your research.
Perfect.
Okay,
That's
thanks. I
super
really
interesting.
have
Thank
to.
you. Thank you.
Thank you. Bye bye.
Bye. Thank you, Henry.
Thanks, Henry.
You're very
Bye-bye.
welcome. Have a nice day.
You too.